Hello guys, in today's video I am going to solve 10 organic problems mainly from the hydrocarbon chapter. I am Dr. Rami Khan and I'm running a chemistry institute at Imphal. Okay, without wasting time I'm starting the questions. The first question is I'm sorry, this number is not in started from 1. The first question is this is propene and if it is reacted with nitrosyl chloride, P is formed. P will be the major product and we need to identify P from the given options. So this is our propene. Okay, this is our propene, and to this propene we need to add what? Nitrosyl chloride. Nitrosyl chloride is NOCl, and the NO will carry negative charge and the Cl will be positive charge. So we need to add chlorine first to have carbocation, and to that carbocation this NO minus will be attached, and this addition will be according to Markovnikov's rule. So according to Markovnikov's rule, negative part of the reagent, that is NO, will be added to that carbon atom having lesser number of hydrogen atoms. So Cl will go to this carbon atom and NO will go to this carbon atom. So we are going to get this product CH3 CHNO and CH2 will be attached by chlorine. This will be our major product. So we need to choose the option from this one. I think second is the correct answer, right? Again, the next question is this is a alkene, and if it is reacted with HBr, then we need to find A is the major product, and we need to choose the option from this. Okay, now this is an unsymmetrical alkene, and when H plus is added, a secondary carbocation will be formed. This double bond will be attached to this hydrogen atom H plus, and we are going to get this carbocation CH3C. This is our CH3, and this will be our carbocation formed by reacting with H plus, right? So this is a secondary carbocation, and to this secondary carbocation one tertiary carbon atom is attached, from which hydride shifting can be done. So we will do hydride shifting to get a more stable carbocation, that will be CH3C plus CH3, then H will come to this carbon atom, this will become CH2 and CH3, right? So to this carbocation, stable carbocation, which is a tertiary carbocation, Br will be attached, right? So to this carbocation Br will be attached, so we will get this as the major product. To this carbocation, Br minus will attack to this carbocation to form this as the major product. So A will be this hello alkane. Okay, let me go to the next question. Let me move my position from here to here. Okay, a hydrocarbon of formula C6H10 absorbs only one molecule of hydrogen upon catalytic hydrogenation. This means what? There is one double bond only. Okay, upon ozonolysis, the hydrocarbon yields this product. This is aldehyde, this is also aldehyde, and how many carbon atoms are here? 1 2 3 4 5 6. So we need to identify the hydrocarbon which yield this carbonyl compound upon ozonolysis. And if we take this cyclohexane, then cyclohexane will not undergo this hydrogenation, so this cannot be the answer. And also this does not fit the formula. Cyclohexane is C6H12. Okay, so this is not correct. Benzene, this cannot be correct because benzene will need 3 moles of hydrogen upon catalytic hydrogenation. So cyclobutane cannot be the answer because this gives a carbonyl of 6 carbon atoms. So our correct answer will be cyclohexane. Let me write the reaction here. This is our cyclohexane. This is our cyclohexane, and cyclohexane have this formula C6H10. Okay, upon hydrogenation, we will get this cyclohexane as the only product, right? And if it is undergone ozonolysis, O3 followed by zinc hydrolysis, we are going to get what? This double bond will be broken, and 2 oxygen atoms will be attached to this carbon atom and to this carbon atom, like this. This double bond is broken, so this will be O, this will be O. Hydrogen is there, so 1 2 3 4 5 6, so this product is obtained. So our answer for this question is cyclohexane, right? Okay, let me go to the next question. An alkene obtained by the dehydration of an alcohol A. An alkene obtained by dehydration of an alcohol A is our alcohol. On ozonolysis gives 2 molecules of acetaldehyde for every molecule of alkene the alcohol A is. So okay, now we need to choose the alcohol, and by doing dehydration, that alcohol will produce an alkene, and that alkene on ozonolysis will produce 2 moles of acetaldehyde, right? So let me ref this one for solving the question. Okay, now we are going to get 2 moles of acetaldehyde, right? This is our acetaldehyde, CH3 C double bond OH, and this is another mole of acetaldehyde, right? So the alkene will be actually what? By connecting these 2 carbonyl carbon atom with a double bond, that will be our alkene, means CH double bond CH then CH3. This will be the alkene which will be produced from the alcohol. So what is that alcohol which will give this alkene on dehydration? So the answer is not this one, because this contains only 3 carbon atoms. Not this one, this contains only 2 carbon atoms. Not this one, because there is already a double bond, and upon high dehydration maybe there may be a double bond also, but that double bond and that alkene will not be stable, and the only option according to the question is this one, because upon dehydration of this alcohol, suppose this is the alpha carbon atom and this is the beta carbon atom, hydrogen will be removed from beta carbon atom, and OH will be removed from alpha carbon atom to form this alkene. So this will be concentrated H2SO4, right, at 443 Kelvin. So the alcohol A must be this alcohol, because on dehydration of this alcohol will give this alkene, and ozonolysis okay, of this alkene will give this 2 moles of acetaldehyde. So this is our answer. Okay, let me go to the 5th question. Okay, the addition of HCl in the presence of peroxide does not follow anti-Markovnikov's rule, because we need to choose the options, the most correct option from this one. Okay, the first one is HCl bond is too strong to be broken homolytically. This is This may be correct. Cl atom is not reactive enough to add to a double bond. This is not correct, because Cl radical is reactive. Okay, and Cl atom combines with hydrogen atom to form HCl. This is also not correct. HCl is a reducing agent. This is also not correct. So the most correct one, according to the from the given options, will be A. HCl bond is too strong to be broken homolytically. Okay, and another reason is also there, which is not given in the options, that in adding HCl to an unsymmetrical alkene, two steps will be there, and one of the steps when HCl is added involves endothermic process. Okay, that requires energy. So it does not follow anti-Markovnikov rule in presence of peroxide, and in presence of peroxide only HBr is applicable. Okay, or anti-Markovnikov rule or peroxide effect is valid only in case of HBr, not for HCl or not for Si. Okay, I'm moving to the next question. The next question is addition of HBr to 2-methyl 1-propene in the presence of hydrogen peroxide mainly forms. Now this is anti-Markovnikov rule. Okay, let me draw this alkene, 2-methyl 1-propene, right? So this is our propene, and to this carbon atom methyl group is attached. This is our 2-methyl propene, right? 2-methyl 1 to 2-methyl propene, right? This is correct. Okay, this is 2. Now if it is added HBr in presence of what? Peroxide is there. Okay, this will follow anti-Markovnikov rule. Now according to anti-Markovnikov rule, Br will be added to that carbon atom having larger number of carbon atoms, and the hydrogen will go to this carbon atom, right? So we are going to get CH3 CH3. No rearrangement will be there, and to this one I think no rearrangement is possible. To this carbon, bromine will be attached. To this carbon atom, bromine will be attached. So this will be our major product. So we need to choose 1-bromo 2-methyl propane. 1-bromo 2-methyl propane. So the fourth one is the answer. Okay, let me go to the next question. Which of the following alkene on oxidation with hot KMnO4 will give only this as the product, right? So for solving this question, I need to rough this one. Okay, now this is similar to what hot KMnO4 is similar to ozonolysis reaction. So if cyclohexene is taken, like in the previous previous question, cyclohexene will produce 2 aldehyde in the terminal carbon atoms, and that will contain a total of 6 carbon atoms. So this will not produce, because we are getting 2 ketone here. So 1-methyl cyclohexane, this is also not correct, because 1-methyl cyclohexane is this one. Let me draw this structure. This is our 1-methyl cyclohexane. So 1 ketone and 1 aldehyde will be formed. This is not aldehyde. Okay, 1,2-dimethyl cyclohexane, 1,2-dimethyl cyclopentane. This cannot be correct. So our answer is this one, 1,2-dimethyl cyclohexene. Let me write the reaction here. This is our cyclohexene, and to this carbon atom and to this carbon atom methyl group will be attached, and if it is reacted with hot KMnO4, this will be broken just like in ozonolysis, and we are going to add 2 oxygen atom with double bond here. So what we are going to get is this product, double bond O to this carbon atom, methyl is attached. Let me draw here methyl, and to this carbon atom also 1 oxygen atom will be attached with double bond, and another methyl group will be attached. Let me draw here, right? So this is the product, I think. CH2, 4 times CH2, 1 2 3 4. Okay, and to this CH2 two COs are attached, CO, okay, and to the COCH3 two CH3 are attached. So this is the correct option, and the reaction is like this. Okay, let me go to the next question. The next question is, what identifies Z in the following sequence of reaction? This is our alkene, and if it is reacted with HBr in presence of H2O2, Y is formed, and Y is reacted with this, Z is formed. So we need to identify Z. So this is pretty easy question. Anti-Markovnikov rule will be applied here. So our Y will be this one, CH3, CH2, and to this carbon atom hydrogen will go, and to this carbon atom Br will be attached. That is anti-Markovnikov rule. So we are going to get this CH2 Br, right? This is our Y, and if it is reacted with sodium ethoxide, then Williamson reaction will take place. This is our sodium ethoxide, right? And this will attack, this is Na, okay, this is Na, I'm writing here. This is our nucleophile, this ethoxide will be our nucleophile to attack, and this will attack this carbon atom to displace this Br. Br and sodium will combine to form NaBr, and our final product will be this one, CH3, CH2, CH2, and CH2. To this CH2, ethoxy group will be attached, O, CH2, and CH3, right? This will be one ethoxybutane, right? So let us choose the correct option from here. This is not one ethoxybutane, this is not one, this is 2 ethoxybutane, this is not correct. CH2 3 times CH3, this is correct. This option C is correct, option 3 is correct. This is also not 1 ethoxy, this is 1 methoxypentane, I think. This is the correct option. So this and this are same, just check. Okay, now let me go to the next question. Last two question. 1-bromo-3-chloro-cyclobutane when treated with 2 equivalents of sodium in presence of ether, which of the following will be formed? This is Wurst reaction, and it was asked in IIT 2005. So let me draw the structure of what? 1-bromo-3-chloro-cyclobutane. This is our cyclobutane, and to this bromine is attached, to this chlorine is attached. And if it is reacted with sodium, then we will get actually this as the product. This is simply Wurst reaction, and if this is Br, also 2 Br are attached opposite to each other of cyclobutane, then also this will be formed as a product. And if two Cls are attached to the opposite position of cyclobutane, and if it is reacted with sodium in presence of dry ether, then also this product will be formed. So our answer to this question is simply this one, right? And last question, this is, I think this is the last question, right? Okay, this is the last question, and for this let me rough this page, this writing. Okay, now this is the question: how many chiral compounds are possible on monochlorination of 2-methyl-butane? Now let me draw 2-methyl-butane, right? This is 2-methyl, this is second carbon atom, and this is our butane, right? This is 2-methyl-butane, and the question is, how many chiral compounds are possible on monochlorination of 2-methyl-butane? Now these 2 carbon atoms are same. Let me change the color. These 2 carbon atoms are same. This is a different carbon atom, this is a different carbon atom, and this is also a different carbon atom. So monochloro product, total monochloro product will be 4, right? and if I substitute one hydrogen from this carbon atom, then we are going to get this CH2Cl, right? We are going to get this one as one of the monochloro product, this one, right? And is there any chiral carbon atom here? Yes, because this carbon atom is chiral now, so one chiral monochloro product is formed here, and another, if I attached from this carbon atom, chlorine will come in place of this hydrogen, so we are going to get CH3C, CH3 to this carbon atom, chlorine will be attached, and ethyl group will be formed, will be there. So this is not chiral because two carbon atoms are same. This methyl and methyl are same. Two valences are same of this carbon atom, right? And if I attach one of the hydrogen atoms here, then also we are going to get a one chiral carbon atom, I think. Let me write here CH3CH, CH3, CH to this carbon atom, chlorine will be attached, and yes, this is chiral carbon atom, right? So two chiral products, how many chiral compounds are possible on monochlorination of 2-methyl butane? So till now we are getting two chiral compounds, okay? And if I attached one hydrogen instead of hydrogen here, then we are not going to get any chiral carbon atom. So only two chiral compounds will be formed from the monochlorination of this compound, okay? So the answer is A, okay? Let me complete this video here. If you like this video, please share this video to your friends, and if you are new to the channel, please subscribe to my channel, and I'll come up more videos on this my channel. Thank you all.